We can now look at colligative properties. Colligative properties depend only on the number and not the identity of solute particles in an ideal solution. Okay, so colligative properties includes number one, vapor pressure lowering, boiling point elevation, freezing point depression, which is also called cryoscope, then osmotic pressure. So there are four. Okay, so we start with vapor pressure lowering. Okay, so here we are just looking at the effect of a non-volatile solute which lowers the vapor pressure of the solvent. So because of the solute solvent intermolecular attractions, higher concentrations of non-volatile solute make it hard for a solvent to escape to the vapor phase. Therefore, the vapor pressure of a solution is lower than that of a pure solvent. Okay, so we can now look at boiling point elevation. Boiling point elevation. Boiling point elevation, which is also called ebullioscope. Okay, so this is the other name. The other name for boiling point elevation, ebullioscope. Okay, that's the boiling point elevation. Okay, so we start with the boiling of the second one is now the boiling point elevation. Okay, so we want to look at the effect of adding a non-volatile solute to a solvent. Okay, so a non-volatile solute, the non-volatile solute solvent interaction. Non-volatile solute solvent interaction cause the solution to have number one, high boiling point, then number two, high boiling point, and also lower the freezing point. Okay, so these are the two effects that we shall look at. Okay, so we are going to draw a graph, or maybe before we draw a graph, where we are now going to write the equation for the change. Okay, so the non-volatile solute elevates the boiling point, So that's the non-volatile non-volatile solute elevates the boiling point, of the solvent. Okay, so the boiling point of the solvent will be elevated. Okay, so the change in boiling point is proportional to the molality. Change in boiling point is proportional to the molality. Okay, so delta T is equal to Kb times molality of solute. Okay, so this is the equation we can use to calculate the boiling point elevation. So where delta T is the boiling point elevation, or the difference between the boiling point of the solution and that of the pure solvent. Okay, in fact here is supposed to be a solution. The one that is elevated, it's the boiling point of the solution and not the solvent. Okay, so delta T is a boiling point elevation. Boiling point elevation, which is the difference between the boiling point of solution, the difference between boiling point of solution and that of pure solvent. Okay, that is delta T, boiling point elevation. Then Kb is a molar boiling point. Molar boiling point elevation constant. Molar boiling point elevation constant. Okay, so this one Kb is characteristic of each solvent. Okay, so it has units of Kelvin or degrees Celsius per mole per kg. Okay, so it could be in kelvins or degrees Celsius. Okay, mole per kg or molar m. Then M solute is a molality of solute. Okay, so having known this equation, we can straight away look at an example. We see how we can use it. Okay, so boiling point elevation, it can be used to determine the molar mass of compounds. Okay, so let's see how we can use it to calculate the molar mass of compounds. Okay. So a solution example, a solution was prepared by dissolving, a solution was prepared by dissolving 18.00 grams of glucose in 150 grams of water. Okay, the resulting solution was found to have a boiling point, of 100.34 degrees Celsius. Okay, calculate the molar mass of glucose. Calculate the molar mass of glucose. Okay, so glucose is a molecular solid that is present as individual molecules in solution. Okay, so glucose is not ionic, it's molecular in nature. Okay, so now we can calculate solution. Okay, so first of all, we need to determine delta T. Okay, so delta T is equal to, remember delta T is a difference between the boiling point of solution and that of the pure solvent. So in this case, the boiling point of solution is equal to 100.34 degrees Celsius. Then the boiling point of pure solvent, which is water, is 100. Okay, 100 degrees Celsius. So when you subtract 100.34 minus 100, it's giving us 0.34 degrees Celsius. Okay, so we know that delta T is equal to Kb m solute. So we need to find the molality. Okay, so molality of solute is equal to delta T over Kb. Okay, so Kb is given, it's a constant. Okay, so the Kb for water is equal to 0.51 degrees Celsius per kg mole. Okay, kg per mole. Okay, kg per mole. So we now substitute. Okay, so delta T is equal to 0.34 degrees Celsius over Kb 0.51 degrees Celsius per kg per mole. Okay, so that is kg, degrees Celsius, kg, degrees Celsius. I'm making mistakes on the units. Okay, so degrees Celsius, kg, degrees Celsius, kg, kb is degrees Celsius, kg per mole. Okay, these are the correct units. I was mixing them up. Okay. Then now we write here kg per mole. Okay, so these are the correct units. So you can see clearly that the degree Celsius will cancel. Then now you divide that, you are going to get 0.67. So this one now will be mole per kg, units of molality, mole per kg. Okay, so we know that molality is equal to mole solute over kg solvent. That we know. Then now what we need here is the number of moles. Okay, so mole solute is equal to molality times kg solvent. Okay, so we know our molality is equal to 0.67 mole per kg times kilograms of solvent. What is the mass of water? Our solvent is water, 150 grams. Okay, so we're going to write 150 times 10 to the power negative 3 kgs. Okay, so you can see clearly that the kgs will cancel. Okay, so the moles of solute, which is our glucose. Okay, so this is moles of glucose. So we multiply there 0.67 times 150 exponent negative 3. So it's giving us 0.10 moles of glucose. So these are the moles of glucose. So if we know the number of number of moles, then we can calculate the molar mass. Since we know that mole is equal to mass over molar mass. Okay, so molar mass of glucose, is equal to mass over mole. Okay, so molar mass of glucose, so molar mass will equal to mass over mole. Okay, so the mass of glucose is 18.00 grams over moles, 0.1 mole. Okay, so 18 over 0.1, we are getting 180 grams per mole. Okay, so that is the number, that is the molar mass of glucose. Okay, 180 grams per mole. So that is how we can calculate. Okay, step by step. So let's now look at freezing point. Freezing point depression. Freezing point depression. Okay, freezing point depression. So the equation for freezing point depression is similar to the one we use for boiling point elevation. So for freezing point, delta T is equal to Kf times molality of solute. Okay, so in this case now, so you can take note, the only difference is Kf and Kb. So here we are using Kf. Okay, so delta T is the molar freezing point depression constant, which is the difference, delta T is a freezing point. Freezing point depression. Freezing point depression. Okay, or the difference. Freezing point depression, or the difference, difference between the freezing point, of solvent, and that of solution. Okay, so since a non-volatile solute will the effect of the non-volatile solute will lower the freezing point of the solution. So it means a solvent will have a higher freezing point than the solution. Okay, so for a good example is antifreeze. Let's look at antifreeze. Okay, we know antifreeze, it's a component in the car's coolant. Okay, the coolant, the one that we put in the radiator. Okay, so when the coolant is added to the radiator in a car. Okay, so let's say during summer. Okay, in summer we know it is very hot. Okay, so now if in the radiator there is only water, and we know that water boils at 100 degrees Celsius. So if you put water on in the radiator, the moment it reaches 100 degrees Celsius, it means the engine is going to overheat. The car will boil up. Okay, it will overheat and damage the engine. So to prevent that, when you add the antifreeze, the coolant, it means now the boiling point of water will be elevated. Okay, so instead of for example, if the boiling point of water has been elevated, or let's say up to, for example, it goes up to 150 degrees Celsius. So it means when the temperature reaches at 100 degrees, the solution in the radiator will not boil. Okay, it has to rise further until it reaches that temperature. That's when now the engine will if it reaches this temperature, that's when now the solution can boil. But also in the radiator, we know we have the fans, the cooling system. Okay, so maybe the temperature cannot even reach there. Okay, so the purpose of the antifreeze is to elevate the boiling point. It goes up. Okay, so as a result, the engine will be cooler in summer. Okay, then in winter we know it's cold in winter. It's cold, then here it's very hot. Okay, so what of in winter? How does the antifreeze work? Okay, so when you add, this is a radiator, when you add water, so in this radiator, this is in winter. So if there is water only in the radiator, it means when it gets very cold, in some countries it goes below 0 degrees. Okay, so we know that the freezing point of water is 0 degrees. Okay, so it means when you put water on in the radiator, when it reaches 0 degrees, what will happen to the water? Ice will form in the radiator. Okay, so to prevent that, we add coolant. We add the coolant, the antifreeze. So antifreeze will be added to the water in the radiator. As a result, the freezing point of water, will be lowered. Instead of freezing at 0 degrees, maybe now the solution can freeze at negative 23 degrees Celsius. So even if when it is very cold, okay, when it is very cold, it will still be liquid water and not solid liquid water inside the radiator. So that is how it works. Okay, so you can see sometimes when ice forms on the tarmacs, sodium chloride is added. Okay, so once the sodium chloride is added to the ice will start melting. It means the freezing point will now be lowered. Okay, so that is how it works. That is how it works. So we can also do some questions on freezing point, depression. Okay, so freezing point depression is also known as cryoscopy. Okay, cryoscopy. Okay, that is just another name for this. Okay, which is given by delta T is equal to Kf m solute. Okay, so that is how this is the equation. So the only thing difference is Kb and Kf. Then delta T is a difference between the freezing point of the solvent and that of the solution, and that of the solution. Okay, so we can have an example. Okay, so let's have an example on the freezing point depression. Okay, so what is the freezing example? What is the freezing point? 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 What is the freezing point of an aqueous solution? Of an aqueous solution when enough sodium chloride has been added to create a 0.25 molar solution. Okay, so the Kf value for water, is 1.858 degrees Celsius per molar. Okay, so M means more per kg. Okay, the units of molarity. the units of molarity. Okay, so we can do the calculation. So here we are dealing with an ionic compound. Okay, so we have delta T is equal to Kf m solute. Okay, that is our equation. So we need to find what is the freezing point. Okay, so delta T. So we are going to write the dissociation equation. We know that sodium chloride will form sodium ion and chloride ion. Okay, so here remember it forms there's a 2 there. Okay, I is equal to 2, okay, which is the Van 't Hoff factor. We are going to come to that, okay. Remember, when we are dealing with ionic and non-ionic, we need to consider that it dissociates in solution. So we multiply it by that value. Okay, so we have delta T is equal to Kf times the molarity of the solvent. So in this case, we have delta T is equal to 2. Okay, 2 times Kf. So the Kf given is 1.858 degrees Celsius per mole. Okay, times the molarity. Molarity is given, which is 0.25 mole m. Okay, so why have we added the 2 here? It's because this one is an ionic solid or salt. Okay, it dissociates in solution, so we need to take that into consideration. Okay, so if it was a non-ionic or let's say molecular, such as glucose, sucrose, I is equal to 1. There's an I here which is equal to so if it's molecular, I is equal to 1. Okay, so for molecular, I is equal to 1. Then for ionic is the number of ions are present, okay, in solution. Okay, so you can see that here it cancels. Okay, so when you multiply now, you are going to get delta T is equal to 0.93 degrees Celsius. Now remember that delta T is a difference between freezing point of solvent and that of the solution. Okay, so delta TF, which is equal to freezing point of water is what? 0 degrees. So it is 0 minus 0.93 degrees Celsius. Okay, which is giving us negative 0.93 degrees Celsius. So this is the freezing point, 0.9 degrees Celsius. Okay, so we can now look at osmotic pressure. Let's look at osmotic pressure. So osmotic pressure is given the symbol pi. Okay, pi, that is osmotic pressure, pi. Okay, so osmotic pressure pi is equal to I mRT. Pi mRT. Okay, so this I it's the Van 't Hoff. Van 't Hoff. So pi is osmotic pressure. Osmotic pressure in atmospheres. Okay, so pi has to be in atmospheres. Then I is the Van 't Hoff factor. Van 't Hoff factor. I is the Van 't Hoff factor. Then M is the molarity in mole per liter. R is a gas constant, 0.08206 liter atmospheres per Kelvin per mole. Okay. Then T is a temperature in kelvins. Okay. That is the formula we shall use for calculating osmotic pressure. Okay, so you can ignore the I if you are dealing with molecular solids. So it is simply pi is equal to mRT. So the I comes into effect if you are dealing with ionic solids. Okay, so we can so osmosis. So here in osmosis, so we know that there's a solvent and a solution. The solvent and a solution. So this side we have solvent. Okay, then the other side we have a solution. Separated by a semi-permeable membrane. Okay, so the solvent and the solution are separated by the semi-permeable membrane. Okay, so what is happening now? The solvent is able to pass through. The solvent is able to pass through the semi-permeable membrane into the solution, but not the solute particles. So it means as a result, after some time, the level of the solvent will go down and the level in the solution will go up, since only the solvent is going into the solution compartment. Okay, so this pressure which is there to stop osmosis is what we call osmotic pressure, pi. Okay, so osmosis is the flow of solvent into the solution. Flow of solvent into the solution through a semi permeable membrane. Okay, so a membrane can be animal skin or vegetable or fruit skins or vegetables. Okay, so that's what happens. Okay, so this pressure now which is there, because it will not continue, so it will reach a point that the pressure in the solvent and the solution will now reach what solvent and the pressure in the solvent and the solution will now reach equilibrium. Okay, equilibrium. So that hydrostatic pressure that is there to stop osmosis is what we call osmotic pressure. Okay, then solutions with the same solutions with the same osmotic pressure. Solutions of same osmotic pressure are called isotonic solutions. Okay, solutions with the same osmotic pressure are called isotonic solutions. Okay, so let's try to solve some examples on osmotic pressure. Okay, so let's have this one. Okay, so when 33.4 milligrams, when 33.4 milligrams of a compound is dissolved in 10 milliliter of water at 25 degrees Celsius. At 25 degrees Celsius, the solution has an osmotic pressure. The solution has an osmotic pressure of 558 torr. 558 torr. Calculate the molar mass. The molar mass of this compound. Calculate the molar mass of this compound. Okay, so first of all, we need to convert solution. So we can first convert osmotic pressure to atmospheres. Okay, that is the first thing you do. So we know that 1 atm is equal to 760 torr. Okay, then we have 558 torr times 1 atm over 760 torr. So you cancel the torr. Okay, so you divide that one. Okay, so when you divide, you are going to get 0.7342 atmospheres. Okay, so always the first thing you do, if osmotic pressure is not in atmospheres, you need to convert it into atmospheres. Okay, so we know that, so we want to calculate the molar mass. So what we need is a number of moles. How are we going to get the number of moles? Okay, so pi is equal to MRT. Okay, so let's make molarity the subject of the formula. So molarity is equal to pi over R RT. Pi over R RT. Okay, so now we also know that molarity is equal to moles over volume. Okay, that we know. So we can as well do this here. Moles over volume is equal to pi over RT. We have not changed anything. Then cross multiply there. So now we have N. N is equal to pi V over RT. Okay, so nothing has been changed. Then now we substitute. Pi, which is osmotic pressure, is equal to 0.7342 atm, okay, atmospheres. Then times the volume of the solution is 10 milliliter. Convert it into liters, okay, into liters, over R 0.08206 liter atmospheres per Kelvin more times temperature 25 degrees Celsius 298K. Okay, 298. So we can cancel the units: atmosphere, liter, liter, Kelvin, Kelvin. You can see we have remained with number of moles. So you multiply on top, multiply down, and divide. So you are going to find 3.00 times 10 to the power negative 4 moles. So these are the number of moles. Okay, so now we know that molar mass. So we want to calculate the molar mass. Okay, so molar mass is equal to moles is equal to mass over moles. So the mass is 33.4 milligrams. 33.4 times 10 to the power negative 3 grams over moles. Moles we have calculated 3.00 times 10 to the power negative 4 moles, which when you divide, you are going to get 111 grams per mole. Okay, so that is our molar mass. Okay, so we can there are so many questions that we can solve on osmotic pressure. So just apply the equation. Okay, so now let's look at the Van 't Hoff factor. Since we have introduced this one, we need to talk about it. Okay, Van 't Hoff factor, I. Okay, Van 't Hoff factor. So Van 't Hoff factor, this was the name of the Dutch chemist. Okay, he was called J.H. Van 't Hoff. Okay, J.H. Van 't Hoff. He was a Dutch chemist, 1852 to 1911. Okay, so he received the first Nobel Prize in chemistry. Received Nobel Prize in chemistry in 1901 for the work that he did. Okay, so the relationship between moles of solute dissolved and the moles of particles in solution is given by the equation. I is equal to moles of solute particles over moles of particles in solution. Moles of particles in solution over moles of solute dissolved. Okay, so we can calculate I. Okay, so the expected value for I can be determined for a salt by noting the number of ions. Okay, so we just look at the number of ions per unit formula. Okay, assuming complete dissociation. For example, sodium chloride. We have sodium chloride. I is equal to 2. Okay, sodium chloride I is equal to 2. Okay, then potassium nitrate I is also equal to 2. Okay, then sodium phosphate I is equal to 3. I is equal to 4. Okay, since they are 4, I is equal to 4. Okay, then for ion phosphate, ion 2 phosphate. Okay, I is equal to 5. Okay, so there are also some expected values or observed. So this is what we have here is expected, but what is observed? What is observed from this? For sodium chloride, observed is 1.9. Okay, then for this one is 2.9. Then for this one is 3.4. Then for this one is not there. Okay, so these are some of the observed. So we have also magnesium. So let's look at magnesium phosphate. So I here is equal to 2. Okay, then observed for magnesium sulfate is 1.3. Okay, so why is it that expected you find that it's higher than the observed? So it's because of there's ion pairing. Okay, so when the ions dissociate in solution, for example, sodium chloride will dissociate to form sodium ion and chloride ions. Okay, so some ions can pair and being counted as 1. So that is why the observed is lower than the expected. Okay, so we can calculate. We can have an example on okay, on osmotic. I think we had one on osmotic pressure. So let's quickly look at degree of dissociation. Degree of dissociation. Degree of dissociation. Okay, so we want to look at degree of dissociation. Okay, so there is a simple relationship between this parameter and the Van 't Hoff factor I for a fraction alpha. Okay, so alpha, that is degree of dissociation. Okay, into any ions. So alpha, that is degree of dissociation. Okay, degree of dissociation, alpha. Okay, so alpha, degree of dissociation alpha is equal to I minus 1 over n minus 1. Okay, that is the degree of dissociation. So we can have an example. Let's see how we can use this equation. So I is the Van 't Hoff factor, then alpha is the degree of dissociation. Example, when the osmotic pressure of a 0.3 molar solution, of magnesium sulfate, what is the osmotic pressure? What is the osmotic pressure of 0.3 molar solution magnesium sulfate? If the magnesium sulfate is 80% dissociated, at 20.0 degrees Celsius. Okay, what is the osmotic pressure of a 0.3 molar solution magnesium sulfate, if the magnesium sulfate is 80% dissociated at 20 degrees Celsius. Okay, so we need to calculate solution. We need to calculate I. Okay, we know that alpha is equal to I minus 1 over n minus 1. Okay, so in this case, our alpha, that is degree of dissociation. So we will divide it by 100, which is equal to 0.80. Okay, you get the decimal percentage. Okay, divide that by 100. That is our alpha. Then now N, magnesium sulfate will dissociate to form magnesium ion plus sulfate ion. So clearly here you can see that N is equal to 2. Number of ions equal to 2. 1 plus 1. Okay, so we make I the subject of the formula. Okay, so I will equal to 0.80, which is alpha. Okay, then times 2 minus 1. So I is equal to 1.80. So that is our I. That is our I. Okay, then now we apply the formula. Pi is equal to I MRT. I is equal to MRT. Okay, so now we multiply there. Okay, so our I is 1.8. Okay, then now we do the math. Okay, so we have 1.80 times M is given 0.30 molar or more per liter. Okay, so you use more per liter so that you cancel the units properly. Okay, then R, we know R 0.08206 liter atmosphere Kelvin more. Okay, then Kelvin more. Then temperature 20 degrees Celsius temperature. So it's okay, so let's just maintain let's just change it to 25 so that we have 298 here, the one which is well known, 298 K. Okay, so now you multiply these numbers, you are going to get you multiply, so you're going to have 12.98 atm. Okay, so that is how we can calculate the osmotic pressure using for ionic compounds which undergoes dissociation. So this formula is very important. So when you are given some dissociation percentage, then you need to calculate I. Okay, so that is how we can calculate. All right, so we can end here. This is the last part of our topic, properties of solutions. Okay, so the next topic that we are going to look at will be communicated. All right, thank you.